morning. Let me start by recalling what we were doing last time. So this is review. So the goal is to prove this theorem 29, which is the semicircle law on small scale. So it says that you can approximate the empirical eigenvalue measure with the semicircle measure up to an error which is with very high probability, or which is stochastically dominated by this 1 over n. And we saw last time this is the best bound you can hope for. And this holds for all intervals. All intervals I. So this is a uniform bound for all intervals. We will see, in fact, that it's not too hard to upgrade this result to a simultaneous bound. So there exists a high probability event such that on this event mu of I is equal to rho of I plus something of order n to the epsilon minus 1. Well, we've talked about this distinction between simultaneous and uniform bounds. Let me not dwell on that now. Let me review the proof, so where we got to last time. So the proof uses, we did already some steps of the proof, and we used the Helfer-Sjöstrand formula, and we arrived at the following formula. So we took a function f. I will not remind you of the precise definition of the function f. So we first assume that the interval is bounded, so it's in this set minus 3, 3. And if this is my interval, I take, this could be my axis, I take a function f which is equal to 1, which is smooth. It's equal to 1 on the interval, and it's equal to 0 if your distance to the interval is greater than or equal to eta. So that was our function f, and then we had a cutoff function chi, if you recall, which was for the y component in the complex plane, and this was equal to 1 in the neighborhood of the real axis and 0 far outside. And with this, we found the following formula. Let me recall the formula we arrived at last time. So mu hat was equal to mu minus rho. So this is a real signed measure that we have to control, obviously. That's the measure we are trying to control. And we found, using the Helfer-Sjöstrand formula, we found the following formula. So we split this integral into 2. And g hat was the Stieltjes transform of this signed measure. So that was the first piece that I called A. And then we have the second piece that is exactly the same, except now I integrate over y's whose absolute value is greater than or equal to eta. Let's say greater than eta. It's exactly the same. I think I probably forgot a y. I forgot a y here. And this I called b. And finally, I had the real part of this term where I differentiate the chi. this term I call C. Okay, so this was the result of this, of the application of this Helfer-Sjöstrand formula, and then we will estimate A, B, and C using, so we of course from this local law we get good bounds on G hat. We know that G hat is small, it's basically stochastically dominated by 1 over n y, or absolute value of y. If you recall, this is there was this slight distinction between simultaneous and uniform bounds. This is a uniform bound, but using the Lipschitz argument that we've already seen, we can upgrade this to a uniform bound. And that was the following observation. So with very high probability for all, so give ourselves an epsilon. If you recall, we had chosen an epsilon. We had an epsilon, and then we had eta, which was n to the minus 1 plus epsilon. Epsilon was fixed. So for all x less than or equal to epsilon and y so y we are considering spectral parameters whose imaginary part has absolute value bigger than or equal to eta, then we have the bound G hat x plus iy. Okay, this was a consequence of theorem 11, the local law, so this is where it comes in, only here. And then a Lipschitz argument that we've already seen to upgrade this to a simultaneous statement. Okay, so this is how far we got last time. Is this okay so far? So this was review from last time. And now what I would like to do is do this program of estimating these terms. You see it's relatively straightforward what one has to do. You will see there is only one place where maybe one could get worried and one has to think a tiny little bit. Otherwise it's mechanical. So let's start with C. C is the easiest. You can stare at these terms a bit, so let's stare at them. C is clearly the easiest. Why? Because it has a chi prime. And chi prime, so the derivative of chi, is supported on the set. This guy has support. Let's look at positive values of y. If you recall the definition of chi, it's flat. It's equal to 1 in between minus 1 and plus 1. So this means that on the support of this integral, y is away from the real axis, and therefore this guy is just n to the epsilon over n. This denominator, which is in general very dangerous, is just not there. And it's very easy. You have f, integration of f, that's bounded. You have an integral of f prime. If you recall, that's also bounded uniformly. So that's basically easy, very easy. So let's do that. So chi prime has support. So now let me be a bit more precise. So it's in minus 2, 2 without minus 1, 1. Okay, by definition. So that C, an absolute value, is bounded by, well, we have this 1 over 2 pi, real part, let's forget about that. The integral of f prime, if you recall, was bounded by some constant which does not depend on n or eta. So let's pull this constant out. Well, in fact, let me do it in a few steps. I don't really care about these constants, so I integrate over x, I integrate over y. I take the absolute values, and so you do it like this. Y, well, y is bounded, so I can forget the y if I wish, but I can keep it for now. This is important. And G prime is bounded by that precisely because of this fact here. And this I can now estimate the integral over y, of course, has to be finite, so this I can estimate just by the indicator function y is less than or equal to 2. So the y integration gives me a constant, and the x integration, so there I can do the y integration, this just gives me a constant, the x integration here gives me a constant, and another constant, and so this is bounded by and this is c times eta. Okay.
Where did eta come from?
Eta, I'm just substituted n to the epsilon over n by eta. I mean, this is eta.
But doesn't f prime depend on eta?
It does, but the integral, if you recall, this was an important fact that we are using, the dx. So that's maybe a good thing to remember. We had this estimate, right? F prime is badly behaved, so the L infinity norm of F prime blows up like 1 over eta. But it's supported on an interval of size eta, so we get that. So that's from the integration over x. Okay. Now, good. So that was C. C was easy. Let us look at A. So A and B require a bit more work. Let's start with A. A has an apparent problem that if you look at our estimates, so this is what we know. We know that G hat is bounded by this guy under this assumption. Right, so we need the imaginary part in the local law, we need the imaginary part to be at least of order eta. Now, if you look at the application in A, then this assumption is clearly wrong. Right? This is not satisfied. We are precisely in the complementary regime. So that looks somewhat problematic. In reality, there's a very simple monotonicity argument that you can make, and that is that this function here, and this is the reason why I wanted to smuggle in the imaginary part, if you recall last time, that this function is in fact monotonically increasing in y. Let's only consider positive y. So in other words, if I replace this guy if I replace y in here by eta, I get an upper bound. And then I find myself in this regime and I can apply the estimate. So let's first, so we only estimate the regime, or the region where, let's only do the positive y's. Of course, you can split this integral into 2 bits, the positive y's and the negative y's, and by complex conjugation, it's exactly the same. So it's analogous. And so this is an important fact. So I claim that y, so if y is now positive, y times imaginary part of g hat, in fact, I will not, it is not true for g hat, it is only true for g. It has to be a positive measure. So okay, so this function, I claim, g is the Stieltjes transform of a positive measure. I claim that this function is monotonically increasing in y. And why is that? Well, this is very easy. Just write up the definition of the imaginary part of g. You get y squared over x. Let's see. I should not use y. I should use some other variable. Lambda, maybe. Okay, so this is the imaginary part of my Stieltjes transform multiplied by y. If you recall, the imaginary part of g is just this with the y upstairs. And this function is an increasing function in y. Okay. So for every lambda, this is an increasing function of y. Mu is a positive measure. That's important. So this is not true for g hat, but it is true for g. This is a positive measure. I take a sum or linear combination of increasing functions. The result is an increasing function. So this is increasing as y increases. Is this all right? So let's see how to apply that. So therefore, let's see, I would need some absolute values. So the imaginary part, so I would need a bound on the absolute value of y times the imaginary part of g hat of x plus iy. Okay. And this I will estimate just stupidly using the triangle inequality as y times the imaginary part of g, which is now positive, x plus iy plus y times the imaginary part of m, x plus iy. Okay, so here I don't use the cancellation between these two factors. I just use the triangle inequality. This is the difference between these two guys, and I just take the plus sign. And now the first one, I can estimate it by this monotonicity. If I increase y to eta, I estimate it by eta times the imaginary part of g x plus iy. And the second one, I know that the imaginary part of m is bounded. In fact, it's bounded by 1. So this is if I want to be safe, I put in a c, but in fact, I could keep a y. Okay. And now I would like to get back to the g hat, if I wish. So I can, since this is the estimate, you see now I managed to get to, oops, sorry, this of course should be an eta. Yeah. So now I've got to an imaginary part of size eta, and I would like to use this bound, and I can do that. By, well, let me not write up, but you see here, if I am at eta, what does this, maybe let me write down the answer, and then this is c times eta, since the imaginary eta, since the imaginary part of g, x plus I eta, is bounded by this guy, so n to the epsilon over n eta plus the imaginary part of m. Okay, I'm just kind of going back and forth. Now I want to use this bound again, and both of these terms are bounded. I hope you can read what I wrote. Okay, so I just, you see, I get here, I would like to show that this guy is bounded by a constant, and I compare, again, I compare G to M. I know that M is always bounded, and the difference between them is bounded by this, but now Y is equal to eta, and I get precisely a constant here. Right, so this n to the epsilon over n eta is precisely bounded by C. Is this all right? So the key idea was to use this monotonicity, which is only true for G, and using that I can deduce that this guy is in fact bounded by the same thing at the value imaginary part y equal to eta. Okay, so now it's smooth sailing. Now you see I just plug this in here, and let's see what comes out. So I would like to, if possible, I will erase the top. I would like to keep these terms on the board. So I will erase what we did for C. Now we are done, basically. So hence, A in absolute value is bounded by a constant. So what do we have? We have the integral over x dx, and then we have the integral over y less than or equal to eta. Then we have f double prime of x. The chi is just equal to 1 on this domain, so I can forget about the chi. And I have now this guy, which I just estimated by eta. Okay, and now we just have to count the powers. So if you recall, the integral over f double prime gives 1 over eta. So this gives me a c, 1 over eta, then I have this eta, and the integral over y gives me another eta. So this is all equal to c times eta, which is what we wanted. Okay. So this was a slight twist. The only thing one had to observe is that here the result is not applicable, but using such a very simple monotonicity argument, you can in fact go up. You can estimate this guy by the corresponding guy higher up in the complex plane, and then you're done. Okay, so what remains is B. So let's do B. So in B, let's try the same thing. So again, I only estimate the region where eta is, y is positive. The negative y's are the same. Y is positive. In fact, y is greater than, maybe I should write it here. Y is greater than eta. Okay, so let's do the same thing. Now this result that I just erased is applicable, right? So we are in this region. We can use, in fact, this was the reason why we split A and B, because we have to use a different strategy. In this region, our estimate is applicable as is. No need to use any monotonicity. So the direct we have a direct estimate, which is the following. B in absolute value is bounded by. So we have the integral over x dx. We get f prime double prime of x. As always, then we have the integral over y. Eta goes from y goes from eta to infinity. Well, I will have this function chi, but let me keep it. Well, in fact, let me use already the fact I have the function chi. I have the cutoff function chi, which means the integral goes only from eta to 2, because chi is equal to 0 after that. And then I have a y. y, and then I have just this guy, which I know is bounded by n to the epsilon and y. Okay? So, this, if you look at it, it doesn't look very good, right? So let's try to finish the estimate nevertheless. So these y's cancel. The integration over y just gives me a factor 2. So this gives me a constant times eta from this n to the epsilon over n. But I still have the x integration, which gives me a 1 over eta. So I lose my eta, and I just get a factor c. And that's a disaster. Right, so this is way too big. Remember, we are trying to prove that this thing is of order eta, in fact, so this was our goal. Epsilon, of course, is arbitrarily small, so we want to get an eta, or n to the epsilon over n. And this is way off. This is basically an empty statement. So here we have a slight problem, and where does the problem come from? Well, sort of intuitively it comes from the fact we are integrating this f double prime here. It was affordable in A because we were integrating over a very, very tiny domain. So this eta would compensate the extra eta coming from here. Now we are integrating over a large domain, and the extra 1 over eta from f double prime is not affordable. So we should get rid of this f double prime somehow. So how can we get rid of the double prime? How can we convert the double prime to a single prime? Yes, do integration by parts. So let's do that. And you see, why does integration by parts look nice? Because x, so if we do an integration by parts in x, this is a smooth compactly supported function, so there are no boundary terms. X only occurs here. Okay, so if we do an integration by parts in x, then we have to differentiate this guy in x. That's not very nice, right? The derivatives of Stieltjes transforms are somewhat nasty. However, because this is an analytic function, it's a function of this argument, x plus iy. Differentiation of this guy in x is the same as differentiation of this guy in iy. So we rewrite the derivative in x of this guy as derivative in iy, and then we can do another integration by parts, but in y this time. And this is much better, because then in the end we shift this derivative in x from here to a derivative in y over these two terms. And that's the key trick. This is a useful trick when working in this formula. It's a very helpful trick that one uses a lot in these kinds of arguments in spectral theory. And this is very benign. We know already if we differentiate the chi, everything is going to be very easy to estimate, and differentiating the y is also quite benign. Here we just have to watch out we get a boundary term, because the integral in y goes from eta to 2. We don't get a boundary term at 2 because of the chi, but we get a boundary term at eta. So this is not good enough. So the solution, we shall integrate, so get rid of f double prime by integrating by parts. I'd like to do this carefully. I gave you the idea. I'm sure if I left you alone for half an hour, you would do this, because I told you already how it goes, but let's do it together. By integrating by parts in x, and then in y. So b in absolute value is bounded by, let me forget these factors of 2 pi and so on. Let me also forget this imaginary part. I can pull out all of this is real. I can pull out the imaginary part from the expression, and then I just forget it in the absolute value. So I have integral over x, integral over y, have, maybe I should write them in the same order, so chi y times y. And now I have the derivative in x, let me write it like this, of g hat x plus iy. Okay, so that's what happens if I do one integration by parts. I have no boundary terms because f and hence f prime and f double prime are smooth functions with compact support. And now I observe that this, when acting on the function g hat, the derivative in x is the same as minus I times the derivative in y. So this was the first integration by parts, and now I do another integration by parts. I will get three terms. One is the boundary term, right? So that's the term when the boundary term here, and so that's the term when y is equal to eta. So let me start with that one. So I have f prime x times this. So I have eta, chi of eta is equal to 1, and I have g hat x plus iy. Okay, that's the boundary term. And then I have two terms that I get by differentiating this, and one is when I differentiate chi, and the other one is when I differentiate y. So let me write them like this. I have that's the term I get if I differentiate the y, and finally I can differentiate the chi. Okay, so that's the result of this integration by parts.
In the first one, that would be the g of x plus y at.
Yes, you are right. Thank you. Good. Okay. All right. So let's now let's analyze them. And all of these three terms are now individually very easy to estimate. And then we will conclude the proof. Well, at least the estimate of this integral. So let's see how that goes. Now I can erase all of these terms. We will not need the term c anymore. So now you can estimate these terms basically by staring at them. So you see g hat at x plus iy. If you take the estimate that we had, we know that this thing in absolute value is bounded by a constant. Okay? The integral over x of f prime in absolute value gives 1, and we have an eta. So that the first term gives just a c times eta. The second term, let's do it in a few more steps. So let's do this integral in the next step. Let me just write down the estimate.
Isn't there still an imaginary part in front of the g?
Yeah, no, I forgot about the imaginary part because I don't need it anymore, and everything here was real. So I can just pull out the imaginary part from the integral, and then because I'm taking absolute value, I just forget it. I could also keep the imaginary part, but I'm just lazy. I don't want to keep on writing it.
No, it's fine. Yeah.
So I can. The imaginary part I smuggled in only because of this monotonicity argument for the term b. And now, sorry, I think I kept on writing b when I should have written a, right? So I apologize for this. I should have. I think we are doing b. No, we are doing b. we did A before. No, I think it was correct. Yes, we finished A and now we are doing B. Yeah. Okay, so let me now, the second term, we can do the x integration already. That just gives me a constant. And then let's do the y integration. So we have an integral that goes from eta. I have the function chi, right? So the chi means I only integrate up to 2. And g hat in absolute value was bounded by n to the epsilon over ny. Okay. And then finally I have the third term, which is very easy because I have the derivative of chi. So I have the integral over x, which gives me a constant. I have the integral over y, which gives me a constant also. All of these, this y is of order 1, this is of order 1, and g hat is of order eta because of the support of chi prime. So this gives me something of order c times eta. And you see the second one is by far the most delicate term. And here you see how this integration by parts helped us. We still have some nasty behavior for y. But now, instead of having to take the sup over y, we integrate over y. And this is a logarithmic divergence, which means I get a log factor of eta. And minus log of eta is bounded from above by log n. So this is in fact bounded by c times eta times log n. So I lose a log factor, but that's the best I can do. Of course, I don't really care about log factors. So the conclusion, putting everything together, if I can estimate the log n by n to the epsilon, that's certainly correct. My epsilon was anyway arbitrary. So this is with very high probability. And this is what I wanted to get. So this is the error bound I'm aiming at. And this is the error bound I got. Now for this integral with respect to a smoothed indicator function in the interval -3, 3. Is this okay? Oh. So now we still have a tiny amount of work just to go back to the original indicator function. This is an easy monotonicity argument. So we replace, if you recall, this was my notation. So this was the smoothed indicator function f of the interval I on the scale eta. And I would really like to integrate with respect to the actual indicator function of the interval I. I still keep, let me still work under the assumption that I is bounded in this set. So it's easiest to do this in terms of lower and upper bounds. So let me derive an upper bound on this guy, and then I will derive a corresponding lower bound. I would like to prove that this guy is bounded from above by rho of I plus something small. And so how do I go from the integral over this indicator function to the integral over this one? Well, this is certainly an upper bound of that one, right? Because this function is greater than or equal to this function, if you recall. In fact, I should probably draw a picture anyway. If this is my interval I will work with this indicator function. So this is f. This is my indicator function f, which is greater than or equal to the smooth indicator function f is greater than or equal to the actual indicator function. So this is certainly an upper bound. And now I used what I just proved, that this thing is equal to the same the same integral with respect to this, well, the integral with respect to the same function, but I change the measure and I get an error term plus something of order n to the minus 1 plus 2 epsilon. And now I would like to go back. I would like to replace this guy with an I. Of course, I can't use monotonicity anymore because this is not bounded from above by that. It's bounded from below. But I can use the fact that this function has a bounded density. And therefore, if I now integrate this function with respect to this measure, which has a bounded density, then the difference between the integral, this integral, and the integral over here is just going to be the maximum of the density times the width of this guy, which is eta. So this is bounded by rho I plus d rho over d x, maybe I should call it. L infinity norm times eta plus, and this thing is bounded by, in fact it's bounded by 1 I think, but we don't really care, it's bounded by some constant. So rho has bounded density. Right, so this is just the Radon-Nikodym derivative. We're using the fact that rho is absolutely continuous with respect to Lebesgue measure and its density is bounded. And therefore I get okay, so that was for the upper bound. It's a very simple argument. The lower bound is basically exactly the same. So let me do that also. Yes?
When you have the derivative of rho there, isn't it just the supremum norm of rho itself?
Well, rho is a measure. I mean, it's this notation. Rho is a measure on the real line,
okay.
And this is the density. This is the density of a measure on the real line is by definition the Radon-Nikodym derivative with respect to Lebesgue measure. I mean, you can use your favorite notations. I don't know if this is.
So it's not a derivative of the density.
No, definitely not. That would be a big problem. But I mean, I regard rho as being a measure.
Okay.
And sometimes people identify measures with their densities, and if you did that, then you would just write. You would write rho. But I think if one is extremely pedantic and if you still remember your measure theory classes, then this is probably the more or less precise way of writing things. Okay, so how to get a lower bound? You see, we would like to do the same thing. Except we can't even start because this is only an upper bound. So now we would need to find a smooth indicator function that acts as a lower bound for this indicator function. And for that, what to do is also clear. We will take this indicator function. So this is an indicator function. So this interval here is I. And this interval here is I prime, which is just I from which I've cut off pieces of size eta at both ends. So with I prime, so if I take I prime, which is, so maybe one precise way of writing it is the set of x's whose distance to the complement of I is at least eta. So you have to be really inside your set I. Is at least eta. Okay, it's just a complicated way of writing this thing, right? So this is the interval. then by definition, this function f, so this is the function fi prime eta, is less than or equal to the indicator function of I. And we can proceed exactly in the same way. And now I use our previous result, which allows me to approximate it with the integral over rho exactly in the same way. And now I do the same thing using the fact that rho has a bounded density. This thing is the same as the integral over I or I prime, it doesn't matter, up to an error term of order eta times the density, but the density is bounded. Which means and that's the end of the proof for the case where I is in this interval. Okay, so this illustrates a series of very general and generally applicable ideas. Is you first do the estimates on these smooth test functions, and then by simple monotonicity arguments, you can go to the indicator, the non-smooth indicator function. Okay, so what remains is a tiny little argument that allows us to extend this to all intervals. Maybe now is a good moment to have a break, and we will finish the proof. We will start next hour with the extension to arbitrary I. You will see it's also a very easy argument, and then we will have finished the whole proof. Okay, so let me continue with this argument and conclude it. So maybe just a summary of what we got. So this epsilon that kept on hanging around was appeared in all estimates was arbitrary. We deduce for all intervals I which are bounded in this set minus 3, 3, mu hat of I is stochastically dominated by 1 over n. That's what we got. So now, how do we extend this to intervals in general? The idea is extremely simple. This is your semicircle, and we understand what happens to intervals in this region. Now, if you have an interval which is huge, it could be even infinite. Let's say it goes from here all the way to infinity. Well, we just break this interval up into two pieces. One which is inside, which goes from here to here, and the other one that goes from here to the outside. And this piece we can analyze. We just did it. And this piece we have, from what we did, follows basically immediately that this piece, so the rho measure of this piece is 0, and therefore the mu measure of this piece has at most mass n to the minus 1. And then you can put two pieces back together again, and you will be done. So how it goes is, so we extend. So the result to all intervals I. So we have proved that mu mu of the full interval minus 2 is equal to 1, the interval of rho, and plus an error term. Of order n to the minus 1, right? This is equal to the mass, the row of this interval, which is equal to 1, because all of the mass of rho is contained in that interval. Okay. So what does this say about the complement, the measure of the complement? We know that mu is a probability measure. So if I take 1 minus on both sides, I get the integral mu of the complement. This gives me 0. So this is... We know that the total mass outside of this interval minus 2, 2 is bounded by 1 over n. And now we can just do what I said, which is to split our interval into 2 pieces. So mu of I split it into this guy, and well, maybe I can do this already I can do both of these in one step. So I'm considering an interval which satisfies the assumptions of our previous estimate. So this is equal to rho of I. Well, formally rho of I intersected with minus 2, 2, but I can just forget about this, because rho is supported in this interval minus 2, 2, plus and rho of this guy, which is equal to 0, and this is equal to rho of I. This is the end of the proof. Okay. So this was a very simple extension. So these arguments, they rely on some basic properties of the measure rho. Of course, the fact it has compact support. Okay. So this is the end of this proof, and this was the first application I wanted to give you. The next one is one of the key features about random matrices, and shows that these eigenvalues, they have a remarkable rigidity property, and this is common to basically all random matrix models. So the question is, so what does rigidity mean? It means that the eigenvalues, of course, they are random objects, they are random points on the line, and they will fluctuate around a bit. But the claim here is that they fluctuate very, very little. So they are strongly confined to given deterministic locations, and they move around much less, for example, than if they were independent points, realizations of an independent random variable. And the underlying intuition, if you wish, is that there's some kind of a repulsion between these eigenvalues. They hate being next to each other. They push away from each other. And it's like if you have a crowd of people, people are relatively solid. If you push them close enough to each other, there is a rather strong repulsion, which just comes from basic physical facts. So, so if you have a large number of people and they push against each other, you can try to shake the whole system, but they will not move much. Whereas if you have a bunch of ghosts and you shake them up, then they will start moving around freely, right? And the analog of ghosts, in fact, is for example, independent random variables. And this could be a good exercise, maybe for next week. You can think about putting this on the problem set. Is the analog the analogous behavior, how much you may know about extreme value statistics. So how much, if you take n independent random variables which have the, let's say, the distribution of the semicircle law, and you ask yourself and you order them, and you ask yourself where is the location of the eigenvalue, let's say, of the point indexed by n/2, so the one in the middle. This guy will fluctuate a lot, in fact, by order square root of n, 1 over square root of n. And here we show that they fluctuate, in fact, by an order 1 over n. So they're very, very rigid. So how much can the eigenvalues fluctuate? So this has been studied a lot. There are many results on that, many quite precise results. I would like to give this rigidity result, which in many ways I think is the most descriptive one and is also the most useful one in many applications. So the heuristic is actually not very hard to guess. So lambda I, it's all about counting functions. So reformulating the fact that lambda I is at a given location, which is perhaps a somewhat indirect, a statement that is, of course, what one wants to understand, but not so easy to work with, to reformulate such statements in terms of counting functions or integrated densities. So it's a trivial observation. So the measure lambda, the eigenvalue, if you recall, I ordered my eigenvalues in a decreasing fashion. So I took my lambda 1, which was lambda 2, lambda n. I think this was my convention. Maybe you remember better than I do. I think I took this convention. If I can find it. Yes, I think this was my convention. Good. So this eigenvalue is characterized by the following thing. So this is the ith largest eigenvalue. What does it mean? It means if you take the empirical eigenvalue measure and you integrate it from lambda I to plus infinity, you will get a mass equal to I over n. This, in fact, is characterized by mu so I include the lambda I. In fact, this is not a unique characterization. This is true for any point. I could put any point E here, which is smaller than or equal to lambda I and strictly bigger than lambda I plus 1. Right? And this would remain true. This is a counting function which takes a step of size 1 over n every time you cross one eigenvalue. Is this clear? This is a very important formula. It's very important to understand this. Is it okay to everyone? Is it clear to everyone? So in this way we can get information about the locations of lambda I. And what's the idea? The idea is we ask, what points would I get here? What values of lambda I would I get if I replace the measure mu with the measure rho? By now we know, thanks to this previous theorem, that these kinds of things are very well approximated by the same thing when I replace mu by rho. So I define typical eigenvalue locations. That's what they're usually called. They are effectively just quantiles of the measure rho. So another way of formulating it, these lambda i's are quantiles of the measure mu, and I will now define quantiles of the measure rho. You know that if your measure has atoms, or more precisely, if your measure has a density which is 0, or has places of measure 0, then the quantiles are not necessarily uniquely defined. And that's why this does not uniquely define them. However, the measure ρ has a positive density, and therefore the objects I'm about to write down are uniquely defined by the following formula. I will call them gamma 1 up to gamma n through ρ is equal to I over n. So this is exactly the same thing. Now I have some, as you see here also, I have some ambiguity. Should I include, should I take this one or that one? If I took this one, then I would have an I minus 1, right? If I take this one, I have an I. And ultimately, none of this really matters, but just to make the formulas a bit nice, I will in fact take the average of these two things, which means I have an I minus 1/2. This makes things nice and symmetric, but this really does not matter. If you prefer, you can do everything I'm about to do without the minus 1/2. So they are uniquely, so these are quantiles. So maybe writing more explicitly, they are uniquely defined by an elementary integral. So you can, in fact, if you want to, you can write them more explicitly. You have to take the integral of the semicircle density and then find the inverse function of this integral. Right, that's how you determine quantiles in general. So this is the integral gamma I to 2, 1 over 2 pi. So dx 1 over 2 pi 4 minus x squared is equal to that. Okay, so this defines gamma I, right? So as I said, you take the integral of this function and then you take the inverse of this function, and that's how you find inverse of this function. You apply it to I minus 1/2 over n, and that's how you find your gamma I. So as far as I know, that doesn't have an expression in terms of elementary functions, but that doesn't really matter. So maybe I can try to draw a picture. So what you do is, so where is gamma 1 going to be located? It's going to be located at the point such that the mass between gamma 1 and 2 is equal to 1/2 over n. Right? So maybe I should draw, okay, maybe I should make my n a bit bigger. So this is gamma 1, and then they come in not in regular spacings, but in regular areas. So the next one, so this area has 1 over 2n. This is gamma 2, and so on. So with the exception of the first area, which is 1 over 2n, these areas all have the same area. And you see that the spacing is not going to be the same at all. In fact, where are these guys going to be at their densest? It's near 0. So this is where the density is at its highest, and therefore in order to get the same area, the separation between two consecutive gamma i's is going to be the smallest. If you are near the edge, then the density is going to be very small. It tends to 0, and therefore you need a bigger separation between these gamma i's. And in fact, it's an easy exercise, which I will not do. I will leave it to you to check the following asymptotic. So for let me only look at the guys in this area here. So I is less than or equal to n over 2. The ones on the left are exactly the same. these guys, they are all, of course, less than or equal to 2, and the distance to 2 is given by asymptotically by I over n to the 2/3. Okay, this is just an easy exercise that you'd get by integrating the square root function. So in particular, the separation between two guys near the edge here is of order n to the minus 2/3, and the separation between two guys here is of order 1 over n. So you have sort of a transition from the edge, near the edge, they are spaced, the spacing is n to the minus 2/3, and as you go into the bulk, the spacing goes to n to the minus 1. And this turns out to be true also for the eigenvalues, and that is the content of the following result, which is the main theorem of this section and called the eigenvalue rigidity. So the claim is lambda I minus gamma I is bounded by. So the formula is very natural. Just to write it down carefully requires an expression that's longer than it should be. So let me first only consider this regime here, n to the minus 2/3. So if I were in this regime, this would be the formula. So this is not the final formula because I don't want to make this assumption, but if I made this assumption, this would be the formula. So this is really how you should read the formula I'm about to write down, like this. However, I also want to include the other i's, and if I want to make this clean, then I have to write it like this, which is just a bit annoying. This is the minimum. But you see, if I is less than or equal to n over 2, then this is the guy that dominates, that is the minimum. And for the other i's, for the larger i's, which are on the left-hand side, it's exactly the same thing, except I replace I by n plus 1 minus I. So this tells you that the eigenvalues are very rigid, and in fact they are with high probability localized around these quantiles, and the error, the error in this localization is in fact comparable to the typical spacing between two eigenvalues. So that means that eigenvalues they can't move beyond the neighboring quantiles up to some small error factors which are in here. But this is a very strong form of rigidity. For example, near the edge, so the largest eigenvalue has to be near 2, and it can deviate at most by an order n to the minus 2/3. And if you are in the bulk here, for example, near 0 or near this point, then it has to remain close to its typical location, and the error is going to be of order 1 over n. So this function here, it's easy to remember because it's exactly the same as the typical spacing of these quantiles, or by this result also the spacing between eigenvalues. Is this result clear? Is that a clear is the interpretation okay? So so this is a rather striking result, and it has many applications, as you may imagine. It has lots of applications. In particular, I mean, it's a major topic in random matrix theory, and its applications to lots of things like communication networks and random graphs and community detection and so on, is to analyze the distribution of these guys here. And this is one of the main tools to do that. This gives you very precise information on the locations of the eigenvalues near the edges. The proof is in fact not very difficult. So we will do that. So the proof basically, not quite, but basically is a relatively straightforward consequence of the thing we just proved. So this local semicircle law, you can kind of probably see why. I mean, the eigenvalues are characterized by quantiles of as quantiles of the measure mu. These gammas are characterized as quantiles of the measure rho. And now we can compare these two quantities. We know that the error between rho of such an interval and mu of such an interval is of order 1 over n. And that's the optimal bound. And from that, we can then deduce information about the relative positions of lambda I and gamma I. Now, there are a few extra ingredients. In fact, the most important extra ingredient is in making sure that there are no eigenvalues here. You see, because even if you knew this result, you know that this guy is close to that guy with an error of order 1 over n in terms of stochastic domination, you cannot say anything about the location of lambda 1. We know that gamma 1 is near 2, right, by definition. However, lambda 1 could easily be in the Andromeda galaxy, and you would not see that from this result. This would be consistent, right? Then if lambda 1 were in the Andromeda galaxy, then you could take this measure here would be 1 over n for lambda 1 for any number here which is huge, and this measure would be 0, but this is compatible with what we just proved. So what we just proved cannot tell you anything about the location of the largest and the smallest eigenvalues. And that is the extra input. But basically, if you know that the largest and the smallest eigenvalues are close to where they should be, so -2 and +2, and you have this result that we just proved, then proving this theorem is easy. So what we will do now and finish next time is prove Abound on the location of the largest eigenvalue. And that is also a major topic in random matrix theory. It is in general, it's a difficult question. It can be a very difficult question. We have developed most of the tools needed to do that. There are and it turns out that the way to do that, the most efficient way to do that precisely, is in fact in 2 steps. The first step is to make sure that this largest eigenvalue has to be in some large interval, -c to c. And that is a separate argument, and that is in fact an argument you are doing in the exercises. You might not have noticed, but you started studying sub-Gaussian matrices, and there's a very, very general and also beautiful argument that you will work through. You started working through this last week, and you will finish working through it this week. That allows you to show that if the entries are sub-Gaussian, then this is true. So the eigenvalues will have to be contained in such an interval -c plus c, which is c is not controlled, c is not 2. It's much bigger, so this does not give you optimal bounds. But nevertheless, it's an important ingredient. And the second ingredient is what we do here, which is a much more precise bound, which says that if you know that your eigenvalues are in this interval -c, c, then in fact they have to be very close to -2 and +2. So it goes in 2 steps, and I would not know actually of a simpler approach. That's the way it seems these estimates have to be done. So the main tool is the following proposition. So we give ourselves some constant c, and the claim is that if the eigenvalues are all contained in this interval -cc, and the way of formulating that, since H is a Hermitian matrix, I say that the operator norm, which you can, this is also the largest eigenvalue in absolute value. So if we know that these things are bounded by c, then I can in fact upgrade this to the optimal statement that they have to be at a distance n to the minus 2/3 of the spectral edge 2. Okay. So this assumption we will prove. You will prove it for sub-Gaussian matrices in the exercises. I think the Johannes can correct me, but I think the proof will be completed in today's exercise, today's problem set. I mean the one that is released today and will be due for next week. No? Yeah. And then we will see in class that in fact the sub-Gaussian assumption is not particularly important, provided one knows something about the local law, which we do. And we will be able to verify this assumption in great generality. Okay, so in fact, most of the work is going to be in proving this proposition 31. So how does it work? We are going to use the local law, so go back to theorem 11, to show that to get precise bounds on the Stieltjes transform if you're outside of this interval minus 2, 2, so we will place ourselves somewhere here, and we will use the bounds that we get from this local law, and if these bounds are precise enough, they allow you to rule out the existence of eigenvalues around this point. The difficulty, and this is in general can be a tricky thing, is to obtain bounds which are precise enough to rule out the presence of even a single eigenvalue. And this, in fact, we've basically developed all of the machinery to do that. So we know how to do that, and I will explain to you how that goes. So before, you see, and if you've done that, then you know that there are no eigenvalues. The reason you also see why I have this C, the local law, if you recall, only works in a rectangle which is fixed, which is a bounded size. I mean, you can try to extend these arguments to rectangles which grow with n, but it becomes a bit annoying and painful. So we usually like to fix the size, so we will be able to preclude the existence of eigenvalues anywhere here, because this is where the local law applies. And beyond this C, we don't have the local law, and we have to use another argument. But that's the idea behind the proof of this proposition. And in order to get precise enough bounds, I claim the following. So we will go back now, we will revisit very shortly the argument that we did last week, or 2 weeks ago, to conclude the proof of theorem 11, which was the how to get optimal bounds on G minus M on the parameter theta. So let me take an E, which is, I only work on the right side of the spectrum. The same, of course, applies on the left side of the spectrum. And I would like to, I will always work in the regime where my parameter eta is less than the distance to the edge. And I claim the following bound. So it looks a bit arcane, but this you will see immediately. The proof is more transparent than the statement. These are just the terms that you get without really thinking hard. So we don't. So far, there's not much thinking. This is what you get from the following very stupid argument. So let's do the proof. So from theorem. If you recall, we have G minus M, was bounded by 1 over n eta. And then we had this equation which I called, which was the self-improving bound, if you recall. It was an equation we derived when we did the proof of theorem 11. So I will maybe not write down all of these formulas. They were a bit lengthy, but or maybe I should recall. So just as a reminder, so the self-improving bound was, so this was theta. So if theta was bounded by n eta to the minus sigma, and then theta is bounded by phi sigma kappa plus eta plus. That was the self-improving bound. And now I will use it somewhat differently. Before I sometimes estimated phi sigma by setting these guys to be 0 and taking the square root of phi sigma. Now I will systematically drop these terms to obtain an upper bound. I will only keep the 1 over square root of kappa. So now I can choose the optimal sigma, right? So if this assumption is satisfied, then we know that, thanks to theorem 11, we know that this is true when sigma is the best possible sigma, which is sigma is equal to 1. And we get theta. So I drop this guy. Dropping the eta doesn't really hurt me because I know eta is anyway smaller than kappa, so that doesn't matter. And then I have phi 1. And if you recall the definition of phi, so I will not remind you of the definition of phi. Phi was this explicit thing that had imaginary parts of m and kappa and eta and so on. And I will just use the lemma 15. Lemma 15 which says that in the imaginary part of m is of order eta over square root of kappa in this regime. So I'm outside of the spectrum, and kappa is greater than or equal to eta, and therefore it tells me that the imaginary part of m is of that order. And this is, I'm just basically copying. So in the definition of this phi sigma, you had the imaginary part of m, which I now replace with this quantity, and then I had 1 over n eta. This was multiplied by square root of kappa, and then I have 1 over n eta. I have the square root of the whole thing, and I divided it by n eta. And you can multiply everything out, and you get that. Okay, so that's the end of the proof. So there's nothing going on here. You just have to go back to what we did and not make any mistakes in copying our expressions. But we didn't really do anything. Okay. Is this okay? I mean, you can check this. Maybe this is something you have to check carefully, of course. But you can believe me, and you should do it yourself as well. I try to do this carefully on my own. You can do it on your own. You just multiply out all of these terms, and you get this up to some multiplicative global constants. Is this okay? All right. So this was a very simple fact. The only idea here to keep in mind is that, well, we go back to this estimate, And of course, now we have the sharp bound on theta. And the idea is we don't want to take square roots of theta. We want to keep the full power of theta here. And the idea is if we are sufficiently far away from the edge, so if kappa is sufficiently large, then dividing by square root of kappa is completely harmless. So that's certainly a much better thing to divide by square root of kappa than by taking the square root. This guy is very small. This guy is of order 1 over square root of n, even smaller. So that's very small. Taking a square root of it is bad. If we are sufficiently far away from the edge, dividing by square root of kappa is harmless. And the hope is that we can in fact make this work as we approach the edge and as we get quite close to the edge. And indeed, these estimates are all sharp, and we will be able to make all of these arguments work very close to the edge. But the guiding philosophy, if you want how one would develop such an argument, is to keep always in mind that if needed, I assume I'm sufficiently far away from the edge, and let's see how close I can get. Okay, so with this, let's see how to prove this proposition 31. So let's see how to prove that you cannot have eigenvalues in this region of the real line. And the idea is a nice one. It is as far as I know, certainly the most direct, perhaps essentially the only way to get bounds or spectral gaps from the Stieltjes transform. It relies on a very simple observation. So let's suppose that so I will suppose throughout the proof that my H in norm is bounded by C. So then we show that the largest eigenvalue cannot be larger than 2 plus n to the minus 2/3. So what's the idea? I'll explain the idea to you, which is very simple, and then the proof is just going to be doing these estimates carefully and making sure that this idea really works. So let's take a number E, which is outside of the spectrum. And we will try to find an eta. Now, the eta is free to choose. We can choose whatever eta we wish. We should try to choose the best one. Such that the imaginary part of G, if so then we want to derive a bound on the imaginary part of G at E with the imaginary part of eta, and we try to prove that this thing is much less than n eta. If we can do this, then we have 1. Why is that? So this is a heuristic discussion, so I use this symbol to be much less than. So if you wish, this means A. So A much less than B means A is little o of B. I only use this symbol in these heuristic discussions. In practice, we always have quantitative factors of n to the epsilon and so on. But this is just to give you an impression. So this has to be much smaller than that as n tends to infinity. Why? So why does this imply exactly what we want? And then the claim is E cannot be an eigenvalue of H. Why? For otherwise, if E were an eigenvalue, we would have the imaginary part of G. Let's compute this guy. This is equal to 1 over n, sum over all eigenvalues, eta lambda I minus e squared plus eta squared. This is just the imaginary part of G. And now I do something very brutal, but in fact this is pretty much optimal if you're on small scales. I drop all of the terms in this sum, so they are all positive, and I derive a lower bound by dropping all of them except the one where lambda I is equal to e, right? I make the assumption e is an eigenvalue, so there is an I such that lambda I is equal to e. And for that term, I get 1 over n eta, right? Because this term is 0, I get eta over eta squared, which is 1 over eta. And this is a direct contradiction to this estimate. So in other words, if I prove this estimate, I know I cannot have an eigenvalue at E. And this is the basic intuition. And you see, I've basically given you all the ideas. Now developing the proof is not particularly difficult. How do we prove such an estimate? Well, all we can do is use theorem 11 that gives us control, in fact, in the form of lemma 3.2. So we have control on G. We estimate the imaginary part of G by the imaginary part of M plus all of this. And then we ask ourselves, is there a range of parameters kappa and eta where all of these terms plus the imaginary part of M is much smaller than this? If the answer is yes, then in that region you cannot have any eigenvalues. We will do that next time. It's a straightforward estimate, and we will find that this works very nicely, and we can precisely rule out eigenvalues which do not satisfy this condition. Okay, so we will do that carefully next time, and then we will be able to conclude the proof of this eigenvalue rigidity result.